Okay, great. So can you hear me at the back? Okay, fantastic. So thank you, Tiger, first of all, for the nice introduction. So the title of my talk, welcome to my talk, which is several neural network models or deep learning models for contrasting meaning representation and semantic composition. So again, I'm Xiaodan from Queen's University, Canada. And I just moved to Queen's University. Before, I was working in National Research Council Canada. Many of this work was done in National Research Council Canada. So, but just to do some self-advertisement. So I'm taking PhD student and a master student. If you know somebody who want to work on deep learning, natural language processing, sentiment, summarization, a lot of different stuff, please contact me. So I'm going to start my talk with a question asked by Marvin Minsky. So in his book, The Emotion Machine, he asked this question like, can a machine fall in love? So if someday machines becomes real intelligent, it should not only be able to clean the room for us, it probably shouldn't have more intelligence like human beings have. But this really is a very, very hard problem. Even I myself was quite convinced that probably some days it's just an issue of time. Probably some days it's going to come into issue, but we probably don't want to argue this problem today because I also have a very bad experience with my wife by arguing this. So it's a really good topic if you want to pick a fight with somebody else. But definitely, even computers cannot understand the emotion or sentiments very good, very nicely. It can already have very good applications. Like if computer can better understand sentiment, emotion, stance, there's a lot of applications. I think many of us are working on different problems using sentiment analysis, stance analysis, and emotion analysis. And so there's a lot of application definitely over there. But again, this hard problem is still there. So it's still very hard for us to net what love is, for example, and how we are going to teach computer what love is. And this is just one concept. But if we combine several words together, the problem can become immediately very difficult. Again, so if we consider combine several words together, the human's language become much, very, very powerful. I just give an example here. With you forever won't be too long. So this sentence do not even mention the word love, but we can feel something, right? So this kind of question is going to be very hard for computer to understand. But finally, the true intelligence is over there. Computer should be able to understand these kind of things, but we cannot solve this problem right now. So this actually involves two fundamental problems. The first problem is how we actually represent the meaning. In this case, love. But how computer actually in general represent the meaning. So the second question is, if a computers can represent the meaning of a word, how computer can combine the word together to represent the meaning of a more complete concept, or like sentences and phrases, phrase levels. So the first problem is called word representation, like word embedding is widely studied in different areas. And the second problem is called semantic composition. So it's a very fundamental problem. Again, so semantic composition is trying to do this very complicated function approximation to combine the meaning from the word level to the phrase level and even sentence level. So that's very, very difficult. Even you use this every day, you express yourself almost effortlessly every day, but you probably do not realize how hard it is for computer. So in today's talk, I'm going to briefly talk about our recent work on both of this, how to represent the word meanings, and how we combine the word meaning to get the meaning of phrases and sentences. So let's start from the basic concept of the word level first. So again, back to this word love. It's an abstract concept. How we are going to teach computer what love is. So what love is. So this is the dictionary we use to teach ourselves. We teach human beings use this dictionary. So you can see, okay, it's very hard to teach computer with this dictionary, even we can teach human beings with this. One reason is because if you see the definition over here, love, there are several aspects of definition. If you check the third definition, love is defined as affection based on admiration, benevolence. So that means the definition of love is entangled with other abstract concepts like admiration and satisfaction, which make things very messy. On the other hand, anger is entangled with fear and hunger. So it's very hard so far to teach computers with this kind of dictionary, but even it's very difficult. Some people, like I myself, are thinking about how to teach the computer with dictionary. Currently, a very popular viewpoint taken by most of people is actually also considered by Minsky himself in his book, The Emotion Machine again. So in The Emotion Machine, this book, Marvin Minsky said, okay, anger and fear are two different concepts. So they have different variables. But at the same time, they share something, so they probably share some variables. And the same things to hunger and thirst. So that means each variable corresponds to different concepts. And also each concept is represented by different variables. So that's exactly what a distributed representation many of us are using right now is like word embedding. So the task here is, okay, now we can represent actually word by a vector. And it's doing many jobs reasonably very well. For example, the meaning has vagueness. The vagueness can be quite well modeled with vectors. But also, word embedding has a lot of strong limitations. So, okay, now we just get the word embedding for sentences. For words, we can use different ways to get the word embedding. So, at the first part of my talk, I'm going to talk about how if we get the meaning of the words, how we combine them together to get the meaning of phrases or get the meaning of sentences. So let's talk about the semantic composition first in this talk, and later I'm going to come back to the word level again to discuss how we learn the word embeddings for contrasting meaning like a sentiment. So the task, for example, is like this. You already have word embedding representation for each word, and how are you going to combine them to get the meaning of the whole sentence? By the way, this is part of the parsing tree. So at the root level, which is the whole sentence, if you can learn these very complete combination functions, you can represent the whole sentence as a fixed size vector as well. And once you get this representation for the whole sentence or for any phrases over there, you can actually do sentiment analysis, of course, and do different things. So the key point here is how to combine the different vectors in word level and get the meaning of the whole sentence. Again, so each combination over there can be very, very complicated. I'm going to talk this in this talk. So in general, if we want to learn this, we follow a principle called the Principle of Compositionality. The principle says like this: the meaning of a whole is a function of the meaning of the parts. It's very important for language because you can consider, okay, the meaning of a sentence is combination of meaning of words, right? But this concept is not just for languages. It's existing in many different places. Like in music, if you are listening to a song, each music notes probably do not have too much meaning. But if you start to combine them together, the songs, the music notes start to make sense to somebody. So instead of random putting them together, you have some function there to combine them together. Even this function can be very complicated, right? So this also happened for vision. Like if in vision, if somebody asks you what's houses, okay, you can think houses maybe there's a roof, at least some windows, probably some doors, right? So it's composed with something which have some meanings to combine together to get some meaning. This also exists in the modern arts, right? If you go to the modern arts museum, probably modern arts do not make sense to everyone, but it makes sense for somebody or for different individuals. That's also because these things are arranged sometimes not by random arranging them together. There's some functions over there. Even the function can be quite complicated. So again, in language, this is already existed. It's a very hard problem. So actually, compositionality is regarded by many as a fundamental problem of intelligence. In a recent paper published by MIT's lab called CBMM, Center for Brain, Machine, and Minds, they emphasize several essential ingredients if somebody wants to build a machine that learn and think like people. So there's 4 ingredients mentioned in their paper. The first ingredient is compositionality. So if a machine needs to think and to learn to think like people. The machine should have this kind of compositionality ability to learn a complicated concept from a simple one. So the second dimension is intuitive physics and psychology along the line of like common sense. The third is learn to learn. So you need to transfer knowledge from one domain to another domain. The fourth is causality models. So I want to make 2 comments for language over here. The first comment I want to make is that many of these challenges actually exist in language. That's why deep learning works very well for image processing, working very well for speech recognition. But language deep learning may not very well work. It's not a magical things for language because there's many hard things to model in language. So many of these exist in language. For example, the intuitive physics of compositionality is in language, right? So intuitive physics is like common sense is also in language. Like recently the Winograd schema test is proposed as a tuning test, right? It's just cross-reference problem. Like we said, okay, the father cannot lift the kids because he's too weak. Who's too weak? Father is too weak. The father cannot lift the kids because he's too heavy. Who is too heavy? The son is too heavy. So father cannot lift. So this kind of questions are very difficult. It involves the common sense. And computer is really very hard for computer to understand these questions, but it's very easy for human beings. So common sense is also in language. And also causality is also in language. Like if we want to do the natural language inferences between different tasks, like 2 sentences, whether the first sentence infer the second sentences, there's causality over there. It's also in language. So it's very, very hard to model these kind of different things in language. This is the first comments I want to make. Language is understanding is very, very hard. Is because there's many of these kind of deep AI problems in language. So second comment is, if you do not believe them, actually they are in your training. When you train a model, you usually complain, okay, I do not have enough data. In many cases, that's just because you do not model this kind of hidden vector very well. So the second comment I want to make over here is that compositionality is actually entangled with other very hard problems. For example, compositionality entangled with common sense. I'm going to give an example later. So also other components also depend on compositionality. For example, if a machine wants to transfer their knowledge from this domain to another domains, the machine should have the ability to compose a simple concept to the very complex concept, right? So basically, this is a very hard problem. Compositionality and the whole natural language understanding is a very hard problem. So I hope I convinced you over here. If you are not convinced yet, I'm going to give you more example. So let's give some example, just narrow down to the natural language, not talking about general artificial intelligence. So talking about languages, okay, today we're talking about like a sentiment analysis way. So consider computer can understand what good is, whether computer can understand what very good is or not very good is. We know that not very good is not equal to very bad, right? So the not is going to change the meaning or sentiments in a very complicated way. Right? So this is the first example I'm going to give over here, and I'm going to go into details with this example by one more slide. So this is a work we published in the ACL 2014. So we want to observe how negation words change the meaning like sentiments. So if we call the whole thing as negative phrases, and we have many these kind of negative phrases in Stanford sentiment tree bank. So we can plot each of these as a dot over here. So the x coordinator is going to be the sentiment of this part. Very good. The y coordinator is the sentiment of the whole thing. So conceptually, if the not change the meaning from the, for example, positive 5 to negative 5, it's going to follow along this line, right? Because it's just this line is just to change the sentiment. If not, again, if the word not changes the sentiment from positive 1 to negative 1, it should go along this line. But actually, you can see the real data, which is annotated by human beings, is not following that. That basically means negation in language is actually a very complicated phenomenon. So I just want to use this one slide to convince you that even one layer of a composition over one dimension of meaning. Remember that sentiment is one dimension of meaning, which is one dimensional semantic orientation, right? So if even one layer of semantic composition over one dimension of meaning, which is sentiment orientation again, it's a very complicated mapping. So this work we done over here saying that. But the problem is we want to combine words, all the words in a sentence together to get the meaning of the whole sentence. You can imagine for some tasks how hard that can be. So I just give an example from good, very good to not very good. Actually, there's other examples, very hard examples over here. For example, senator, former senator. So former senator does not mean it's not senator again, right? And basketball player, short basketball player. So we are not sure mean that the player is short. It's just it's short compared with other basketball player. So you can see this meaning is context dependent. And Barbara Party in his very nice paper also give another example like this, small giant. So giant is a vague concept, and small, like short over here, it's context dependent. So these phrases involve two concepts. One is vague concept, like a giant is vague concept, and another is like short is over there. So small here is context dependent. So Barbara Party argued that like a vagueness in the meaning and the context dependence are two different things. So this example have both of them. And another even more tricky example over here is empty. So we know if I tell you, okay, this bucket is half empty, this bucket is half full, it probably means they are similar to each other, right? Same concept. But how computer can know that? Because empty is different than full, it's different from full. But if you combine this empty and full with word half, if you compose them together, it's become the same concept. So this needs common sense, right? Like I mentioned earlier, semantic composition can involve different aspects of artificial intelligence. So that makes the problem very, very hard. Again, for sentiment analysis, probably we won't involve all this kind of problem. We probably just involve this kind of problem or some other problems. So I want to make a comments over here like this. Those problems is very hard to solve so far. Probably we can solve it some days in the future, but use deep learning models, we can model some of these phenomena very well. For example, the vagueness of the concept, and also probably the negation function in sentiment analysis. Use deep learning models may model this reasonably well. So okay, so this is some examples. Now we just go into reality. How we are going to compose the meaning of the words to get the meaning of the sentences. So most simple model you can do is just to use a linear array scan, right? You can read the word, for example, this sentence has 7 words. So you can read the first words, read the second words, combine them with the first word, and read the third words and combine it with the memory, which is about the first and second words, and combine this, and finally you get the last representation, which is the representation for the whole sentence, right? So you can get this representation for the whole sentence by just run a linear chain SVM. But the one piece of work I'm going to talk today is recursive model. So because we know that for language and for many modalities like images, the data is not just a sequence. The data have some structures. Like for images, you have the buildings have the roof, have the window, the windows have and the doors, and the window have different part. And for language, we have structure as well. So in one of our models, we propose to model the composition process not by sequentially, but over these recursive structures. So there's 2 reasons to use a recursive structure over sequential model. The first reason is because okay, somebody may argue that sequential model probably can learn this kind of structure implicitly, but the assumption is you have enough data. But usually we know that in many cases you do not have enough data. And second case, the reason is that okay, you can regard the sequential model as a special kind of structure model, right? A sequential model, you can think of sequential model as a very deep tree, right? Without any input information. So it's a kind of special case of the tree model because so sequential model you can arrange them as regard them very deep tree. So that deep tree do not have any like syntactic information. But for this syntactic parse tree, you have input information. So the worst case, if the syntactic parse is very noisy, it's probably should not hurt you too much because you basically just need random noise. So that's the second reason. Again, the first reason is you can in this recursive model can provide some ways to model the input structures like the parsing trees. which is given to you as a prior knowledge. That's the first reason. So the second reason is the worst case is parsing tree is very noisy. You just regard it as some random noise, right? You do not have too much bad effects, right? So now I'm going to talk some models we use to combine the meaning of words to get the meaning of the whole sentences. So this is a paper we published in the ICML 2015 International Conference on Machine Learning. So we proposed to extend the non-short-term memory to over tree structures. We called it a tree LSTM. So basically, we know the LSTM, chain structure LSTM, have very nice properties to model the long-distance dependencies over sequences. And now we propose to extend that to tree structure, so we can model the long-distance dependencies over tree structure, not over sequences. This is a traditional chain structure LSTM in different years. They have different version. And our tree LSTM is just some simple extension of them to, instead of you have one memories about your past history, you have two memories, one about your left child, one about your right child. So that two memories combine the information from left child and right child, and then you can compose them to get the new representation over a tree node, right? So this is one difference, one major difference of tree LSTM and the sequential LSTM. So these are some details. I'm not going to go to details, but I do want to make a comments over here. Is that sometimes your tree is not a binary tree. So how are you going to handle that? So the simple trick to do this is, if your tree is not a binary tree, you can just simply to binarize the tree. Because even you binarize the tree, you can introduce some noises, but basically the tree structure is still there. So in that way, you do not need to design. If you binarize your tree, you do not need to design the different nodes, different parameters for different nodes. You just still keep this parameter keep this parameter shared between different nodes. That's a good property of recurrent and recursive neural network, right? The basic idea of a recurrent network is every node shares the parameters. And if you binarize the trees, you only need one type of design for the nodes that can be shared between different nodes. So again, the trick is here is if you have a trees which is not binary trees, you can always binarize your trees and then use the model. So again, we just design this tree structure LSTM, and then we insert them to this composition process. Every node here now is equipped by this. So then now you can combine the meaning of the words to get the meaning of the whole sentences, right? After you get that, you can definitely do the sentiment analysis, but you can feel free to do other things as well. You can use this. I'm going to talk later. So once you get the representation for the whole sentence, you can use them to do different tasks. This is the results. We use these models on sentiment analysis. This is the result on Stanford Sentiment Tree Bank when we published the paper in 2015. The tree LSTM models. By the way, this is accuracy over Stanford Sentiment Tree Bank. And probably many of you use this data set as well. So LOOT is the sentiment classification for the LOOT, which means the whole sentence classification for every node in the tree. So we can see the model is right away it's with a quite large margin, better than the RNT model proposed by Richard Socher, which is a recurrent neural tensor network using tensor over there. So the tree LSTM seems to be very good for sentiment analysis here. So not only that, we also use tree LSTM on different tasks. For example, we use tree LSTM to do the natural language inference. The task is basically to decide the informal logic relationship between two sentences. If I told you, okay, I buy a car yesterday, that probably means I own that car today. So buy means own, right? So this is a simple case, but a more complicated case is we need to infer the relationship, logical relationship between two sentences. So we also apply the tree LSTM to solve this kind of task. And we have a paper in this year's ACL, which is we add tree LSTM to the best previous model, which is also our model. So we do the inference by building two models. One is sequential inference model, and another is add our tree LSTM. So it's improved the performance quite nicely. So again, tree RSTM models we proposed here is to try to combine the sentiment, the meaning of the words to get a meaning all the way for the sentences. And once you get the meanings, you can apply them to different tasks. So actually, we have a tutorial in this year's ACL. It's called Deep Learning for Semantic Composition. This talk is given joint with Edward Greenfested from Google DeepMind. So we have roughly like a 300 to 400 audience. It's a quite large audience to attend our tutorial. In that tutorial, we talk about do the composition using formal method like first order logic very briefly, and also use other neural networks like a recurrent neural network, recursive neural network. Today we talk only about recursive neural network, but in that talk we talk also convolutional neural network, unsupervised models to combine the meaning of words to the meaning of the whole sentence. So by the way, the slides are available on my website already, and the video will be I think the video is going to be released soon. And once the ACL releases the video, we're going to put it online. So this is the first part from my talk. I want to talk about how we teach computers to combine the meaning of words to the meaning of a whole sentence, to get the meaning of the whole sentences. So in that tutorial, there's much more detailed information, including not do compositions over from word to sentence, but you can do composition from subword component to word. The second problem I want to talk today is in many problems, people assume that, okay, we're going to learn the meaning of the whole sentence by combining the meaning of the words. But in many cases in language, we know there's non-compositionality. For example, the phrase is kick the bucket, right? We know the kick the bucket means somebody died. So you cannot learn the meaning of the kick the bucket from the meaning of the kick, the three words, kick the bucket. And for sentiment analysis, you have probably somebody tell you, okay, this restaurant is a must try. So it means, okay, this restaurant is good. Usually means, but you can probably not learn the must try is positive based on the word must and try. So in this case, I call this a hard non-compositionality problem. And I call this soft because some phrases, this is in dictionary, it's a idiomatic dictionary, they have fixed meaning, and some of them is not in dictionary, but it's they compose their message softly or they are non-compositional softly. So I call this a soft case. So this kind of composition, non-compositionality is a common phenomenon in language. So it's existing in different granularity of text. It's, for example, you can basically think at words, the meaning of words can be recomposed from the subword components like the morpheme, right? So it's exists in different layer of languages, right? All the way from the characters levels to the document level. So a framework that can consider this during the composition is very interesting theoretically, right? Because if the model can consider this property, if this phenomenon is prominent, we can model that. And I want to also talk about the programmatic viewpoints. Because remember, for sentiment analysis, sometimes we can learn the sentiment of phrases or n-grams from a very large corpus, for example, from Twitter data. So once we learn the sentiment of whole words, whole phrases, like not a must try, not a must try. We do not need to compose them using to model this composition function. We can just use, for example, not must try as a whole phrases, and we learn their sentiment from very big corpus. So I'm going to talk this. So again, so the programmatic viewpoints is sometimes you can learn the sentiment or meaning of the n-grams from very large corpus. And in that case, probably you want to consider this information holistically, and instead of compose them from each word. And in addition to consider composition from word level to the top level, you can also consider the decomposition, right? So when you backpropagate your errors, you can learn the meaning representation for words. And in that case, you probably don't want to learn the meaning of the kick over here from the kick bucket, because you cannot learn the meaning again. So you probably don't want to confuse your word embedding by learn its meaning from the kick bucket, because you basically should not be able to learn the meaning of kick from the phrases kick the bucket. That's another viewpoint. You just think about top down instead of the composition, you do decomposition. So so we do have So the basic idea is for example, we just talk about composition models over tree structures. We just extended the models a little bit more. For example, each node here, we extended into this node. So this node is considered, okay, whether I'm going to have two information. One is composition information from the children. Another is if we have external knowledges from outside, our model should have some black box over here to model this process. Right? So I just put a black box over here, but in your models, you probably can insert different type of neural network to combine the meaning that learned from its constituents and from outside. So this is a basic idea, again, so you just enable each individual composition operation to have this ability to choose the information they trust more, either from external knowledges or from the compositional knowledges. Right? So this is just basic idea. So we have three models implemented in our paper. The first model you can just implement, or very simply implement this node as a regular one-layer feed forward neural network. So this is model one. So model two, so you can use a Richard-Sauter's tensor-based network to implement this part. So some of you probably have already know this model. So you just insert tensor-based model over here. The third models, we also use some gated models to replace this. Basically, we have two pieces of information, either from compositional or from non-compositional resources over here. We use them to gauge each other. So try to decide what information we should let in to the parent nodes. So we implement this three model. Again, you can use different layers models over here. You can even put multiple layers over there. So this is experiment setup. So we test our algorithm on Stanford Sentiment Tree Bank, and for these non-compositional knowledges, we learn them from Twitter. So because in tweets we have these emoticons and hashtags, so we can use the emoticon hashtag to learn the sentiment of n-grams, right? If n-grams is collocated with the positive emoticon, probably that n-gram is positive. So basically, that's a basic idea. I'm going to skip the details of this, but basically you can use this free but noisy dataset, train the sentiment of n-gram, and incorporate that n-gram into your model through over here. So we test the result on Stanford Sentiment Tree Bank, and we see some moderate improvement. But again, the improvement, the amount of improvement depends on the property of non-compositionality, right? If your data have more non-compositionalities, you probably get more improvement. Otherwise, you get less improvement. But the key idea is here is that this kind of model can consider both compositionality and non-compositionality when the model learns the meaning of the whole sentences. Right? So another example I want to give you is before this model is dependent on the parsing tree structure. This is a parsing tree, right? Give it a tree structure. For some data set like Twitter data, parsing is not very reliable. So if you do not have parsing tree, how can you incorporate this kind of non-composition knowledges into your model? So in another paper we published in NACO, North American ACL, we actually designed a specific LSTM structure called DAG structures to incorporate this kind of information. The key idea is like this. When the computer reads the sentence from left to right, they read the first word, second word, third word, fourth word, fifth word. So they combine, the one choice they can combine this word sequentially. Another choice is, again, we do not have parsing tree here because parsing tree is not very reliable for Twitter data. Instead of compose the meanings from each word, the system also have a true choice to go to other path like this path. To say, okay, because I can learn must try from the other external logic corpus, I probably can let the system to choose which path it should go by just composing the meaning from each of the single words, or just go to this long compositional block over here. Or even better, if the model know what not must try is, it probably can just go direct jump from here to not must try and use that to get the meaning of the whole sentence. So again, it's a software decided. So the system have the computer have the choice to combine, to do this way, and do this way. Again, in this way, the computer do not need to learn the composition, the very complicated composition function from not, must, try. Remember we talked earlier that not is very nonlinear. It's quite nonlinear in functions, right? So the computer have choices to do this, and you can train this whole model end to end to optimize your object function, right? So this is a basic idea of this. I just quickly go through the several node, how we implement them. This is blue node is just a regular memory block, so there's nothing new from there. The second type of node is this kind of non-compositional nodes. This is some representation you can learn from external knowledge, from external data. So you can then, once you get some vector representation for like not must try or must try, you can insert them here. And then I mentioned that here that the dimension of this is not necessary to be equal to the dimension of this, because for example this is 100 dimension. This can have 4 or 5 dimensions. That's fine. The third node is called fork nodes. So basically, we'll pass the information to different outgoing path over here. So this is a fork nodes. The only difference of fork nodes and those regular nodes is when you do back propagation, you have to take the errors from different paths. Another little bit tricky node is this kind of merging nodes. So the merging node is going to merge all the information from different paths. So again, if the number of input paths is different, so you have to design different type of merging nodes. But that's probably something you want to avoid because you want to share the parameters. So so remember the trick we talked about earlier is binarization. You can also do the binarization over here. So instead of doing this, you can binarize the merge to binarize merge. So you can do the binarize merge. And again, the benefits is you do not need to design different nodes for different fan-in, which is different number of input edges. You just design one type of merge node, and you can share them over the whole network or for all this kind of merge block, right? So we do experiments on SemiVal 2013 and 2014 sentiment analysis task. And the evaluation matrix is a standard evaluation matrix. It's a macro F. And this is a result. So our DAG error scan is better than the best previous system. The main message here, I mean, just a take-home message here is like DAG error scan have two advantages. Compared with error scan, which do not have incorporate this kind of external edge, is DAG error scan can consider this kind of external knowledge about the sentiment of phrases, right? Because this best system, some of this best system is also from us. When we built this system, we found that use this kind of external knowledge like n-gram, sentiment for n-gram is helpful. So standard errors cannot consider that. But if you use DAG structure over here, you can consider those kind of external knowledges, non-compositional knowledges. That's the advantage of DAG error scheme over regular error scheme. The advantage of DAG error scheme over the previous models, which is like SVM models, is because error scheme compared with SVM, which is bag of words, bag of phrases, can consider this kind of compositionalities in a very nice way, right? So that's a take-home message again. DAG error scheme is better than error scheme and also better than the traditional SVM, which also use external managers. So, so this is some Appellation results. So basically, if we remove each of these edges over here, we consistently saw the performance is gonna drop. So I'm gonna skip the details, but if you want to know the details of it, you can check out paper to see how these different paths affect the performances. So. This is the second problem I talk about today. So I talk about compositionality, I talk about long compositionality, and the third topic, which is the last topic I'm going to talk today, is okay. So far, we learned the meaning of the whole sentences by combining the meaning of the words and get the meaning of the whole sentence. But if you backpropagate your errors to the word level, you actually can update the word representation, right? And then you can learn the word representations for sentiment analysis, right? Because the word representation for sentiment analysis is different from word representation for other tasks. So you can learn the word representation in this way. But that can be, if you learn in that way, that can be, what you learn can be probably quite ad hoc or data dependent. So in the third part of the talk, I'm going to talk about how we train actually word embeddings directly from lexicon and directly from the corpus to teach them to answer the contrasting meaning questions. For example, some of us probably take the GRE test before when we go to graduate school. One part of the test is, okay, you are giving a questions, you are asking what's the most contrasting words in the multiple choice questions, right? So for this case, the choice is this. So if the computers can learn the meaning of the words, it should be able to answer this kind of question. So that's why we want to, at word level, we want to teach the computer to learn the word meanings to answer these kind of questions. So let's just revisit the word embeddings in most framework like Word2Vec and Glove. So at word level, we know that most embeddings focus more to modeling the semantic similarity or relatedness, right? So by semantic similarity, this is the example. Good is similar to excellent. And for relatedness, we say that nurse is related to hospital, but nurse is not similar to hospital. It's just they have semantic relatedness with each other. So regular word embedding models is pretty good at doing this to learn the semantic similarity and relatedness. But regular word embedding, for many of us, you already know that it's not doing very good to capture these contrasting meanings well. For example, for sentiment analysis, like love and hatred, and another example is active and passive, or the strong and the weak. So this three dimension is actually found by Charles Osgood in his very long old paper. They basically found, okay, for three dimension of you can basically find the connotative meaning of adjectives from this three dimension. One is called evaluative. It's basically a word like good and bad. Another dimension, which is another dimension, is quite independent dimension. It's active words and the passive words. And the third dimension is strong, word about strong and a word about weak. So this is all about contrasting meaning. So we want our word embedding can learn this kind of contrasting meaning. So why those kind of regular word embedding cannot capture this? The reason is like this. So remember that semantic similar words occurs in similar context, but also words with opposite meaning tends to appear in the similar context as well, right? For example, the word good and bad, also their context is very similar to each other. So that's why if you just use the regular word embeddings, you cannot tell the difference between these two. But in sentiment analysis, or if you want to answer these kind of questions, we have to teach computer to do this. So basically, the general idea is, okay, when you do your word embedding, you have to choose which information you are going to lose. It's a lossy, right? But regularly, the models choose to lose information about the contrasting meaning. But in many applications, you need to recover that. So how are we going to model this? First of all, contrast meaning is the very basic aspect of semantics. So that's why we are interested in model them. We give example like a contrasting meaning is important for sentiment analysis, emotion and stance analysis, but it can be used in different places, like the natural language inference. For example, I tell you like a house price in Halifax rose almost 10% last year, or another sentence is Halifax house price decreased slightly in the past year. So we right away human beings know, okay, these two sentences is contradicted to each other. But if computers do not know these contrasting meanings, the computer cannot tell this. So basically, contrast meaning again is a basic aspect of semantics, and it's not only used for sentiment analysis, emotion analysis, stance analysis. It can be used in different places. So that's why we want to model them. So I just very briefly go to a model at a very high level. The models we designed to model this. So the model is we published in the ACL 2015. Its model contains two parts. The first part we use corpus to learn something, the first part we use lexicon to learn something, because lexicon also encodes some human knowledges. So this is the high level of the model. I'm going to just very quickly go to some details. So the first component is called Corpus Relatedness Model, which is this model. This model is good. The basic idea is going to read information from the corpus and try because we like a word vector or globe, these kind of models they cannot tell the difference between contrasting pairs and similar pairs. They cannot do that, but you can use these kind of models to tell the difference between both of the contrasting pair and similar pairs with other pairs, with unrelated pairs. So again, this first model is called Corpus Relatedness Model. It's designed to model the relatedness. So again, the relatedness do not tell the difference between good and bad, right? So you can still use this model to tell the difference between the related concept and the unrelated concept. So this is the first part of the model. For this part, you can just pick whatever you like, for example, word to vector or globe that can serve this purpose. So the second model is SDR. So it's semantic differential reconstruction. So which is this part? So this part is based on these heuristics. Like we know that Osgood have published a paper which identified that 3 dimensions of semantics count for most of the variations in the connotative meaning. So these dimensions, one dimension is called evaluative. It's a word like a good and bad. So another dimension in Charles Osgood's paper is potency. Potency is another dimension that can capture the variance of the connotative meaning, which is strong and weak. And the third dimension is called activities, which is basically many words about active and many other words about passive. So this is 3 dimensions about the contrasting meaning as well. So we also try to incorporate this kind of information to guide this system to tell the difference between the contrasting meaning. So this is the second model. So this is just a high-level idea. We incorporate this kind of knowledge to do this. To learn SDR, we actually use Google's 1 billion words corpus to compute this semantic differential scores over these 3 dimensions by using the Peter Turney's previous work. Peter is, by the way, is my previous colleague in NRC. So the third word knowledge we want to use is human knowledge, because humans encode a lot of their knowledge in dictionary, right? Why not use them? So the basic idea is we want, if in human dictionary, if the word good and bad is regarded as antonym, their embedding should be further from each other than the unrelated pair. Again, so we incorporate the human's knowledge by saying, if human believe these 2 sentences, good and bad, are antonym, in their embedding, we will encourage this their embeddings to further than the unrelated word pairs. So if we put them further, and if we know the excellent is close to good and the awful is close to bad, so the word excellent and awful, it should be further as well, right? So we put these 3 models, train the whole system all together. So we tested them on this on the data set that we just mentioned earlier. It's a GRE contrast meaning test set. So there's some previous work. One is by Microsoft Research. The performance is roughly 81, and by Columbia University IBM, the performance is roughly 82, and by Toyota Technology Institute, the performance is this. So our models get when we publish the paper, it's best results. It's roughly the F1 score is 0.92. So it's not it's perfect, but reasonably good. So if you want to know the details, please check our paper published again in ACO 2015. Okay. I guess that's the main message I want to convey in my talk is 3 parts. The first is we think compositionality is a key problem for sentiment analysis, for contrasting meaning, and for general semantic analysis. And deep learning do provide a very powerful approximation for these kind of very complicated underlying functions. But we also give you some example to try to convince at least I convince myself, hopefully convince you that deep learning still have some problem to solve if you want to solve the semantic composition problem. So the second message notes that we put in this talk is we should model the non-compositionalities in languages. And third, I discuss the word level contrasting meaning. How do we model them? So there's two related talk with this. The one is I mentioned is deep learning for semantic composition is a tutorial we gave in this year's ACL. So the second tutorial is we gave 3 years ago in EMLP. It's sentiment analysis of social media text. It's also related to this. In this talk, we not only talk the sentiment analysis for message, but also talk about aspect-based sentiment analysis. Because for many of these texts, we get very top performance in the competition. And one important thing is in that tutorial, we also mention many very useful sentiment lexicons and resources. If you want to do research in sentiment analysis and emotion analysis, you can probably find some useful resources over there. So future work, I very briefly discuss over the future work. I think I'm running out of time. So future work is, I think, this is some things I'm interested in thinking of. So the first is doing unsupervised model for composition. In our tutorial, we talk about, I mean, not this talk, in our tutorial in ACL, we talk a lot about the unsupervised model for composition. And also compositionality with other ingredient of intelligence I talked earlier today. I think that's very important, interesting to me. If we want to do compositionality very well, we have to consider these hidden factors like common sense, those kind of things. The third is compositionality in multimodalities. The fourth is distributed models with symbolic models like traditional logic models. And we also want to also think about or keep some explicit structure in word level representation, because if you compact everything into vectors, it's good for some things, but for some other tasks, we still need to think about better representation. And probably you got more ideas in your mind already, and I'm very glad to discuss with you either offline or right now. So thank you for your time.